Imagine you are throwing a party. Everyone is enjoying, but suddenly a guest asks for a pizza because they are starving. So, what do? You pick up the phone, call the delivery service, and place an order. They take their time to prepare the pizza and then delivers it. After watching one person eating the pizza, another guest also wants pizza. So you repeat the process. Call the delivery service, wait for them to bake and deliver again. Now this works for a small party. But what if your guest list is huge? Calling the pizza place every time is not only exhausting but also inefficient. Wouldn't it be smarter to order some large pizzas in advance and keep them ready? That way you can serve your guest instantly whenever they are hungry. Well friends, that's exactly how caching works in tech world. Instead of fetching the data from database every time, caching keeps the frequently requested data ready to serve in a fast access storage. In this video, we will explore how caching supercharges the applications and prevent the bottlenecks. From the basics of caching to real world examples of how tech giants like Amazon, Facebook, and Netflix leverage it, and even the challenges they face. So let's get started. You know what's cool? Caching isn't just in our applications, it's actually everywhere in our computers. Let me show you. Think about your computer's CPU, the brain of your computer. Even though your computer's random access memory is super fast, it is still not quick enough for the CPU. That's why CPU has its own mini storage areas called L1, L2, L3 and L4 cache. Just like how we kept those pizzas in the kitchen for quick access, the CPU keeps its most used instructions in these caches so it can grab them instantly. Let us just see the formal definition of caching. Caching is a technique used in computing to store copies of frequently accessed data in a temporary but high-speed storage known as cache. This allows subsequent requests for the same data to be served faster because in that case, data will be retrieved from the cache instead of recomputing or fetching it from the slower underlying source such as database or any remote service. Imagine we have a social media app like Facebook or Instagram with millions of users. In this app, users often request to view the profile details multiple times. Now, if we fetch this information from database every single time, it can take a lot of time, especially when millions of users are doing this concurrently. This will lead to high latency and slower response time, making the app feel sluggish. Frequent database hits or repeated computations can really slow things down. Every time your app makes a call to the database, it has to process that request, fetch the data and send it back. Now, if this happens over and over again for the same data, it puts a lot of load on your database and backend servers. This not only increases the time it takes to respond, but also makes the whole system less efficient. Now, let us see a few real world examples where tech giants faced issues before caching was implemented. In its early stages, Facebook struggled with slow page load as its base user rapidly increased. Each time a user loaded their newsfeed or profile, the system used to fetch data directly from the database. That led to high latency. To fix the issue, they used an open source version of Memcached to build a distributed key value store. This significantly reduced the load on their database and improved the response time. Not only Facebook but Amazon also faced a challenge with high traffic during sale events like Black Friday. Every product view or recommendation required a database query, which was causing delays. By caching frequently accessed product details and user sessions, Amazon improved the page load times and enhanced the user experience. Now, there are endless stories like Twitter, Netflix, and many more. But the main point is how implementing caching transformed these systems, making them faster, more scalable, and capable of handling millions of requests efficiently. Caching is not just an optimization, it's a necessity for modern high traffic applications. Let us see how browsers use caching and improve the user experience. Imagine a world without browser caching. When you visit a website, your browser would download all the resources like images, style sheets, scripts, and other files from the server. And let us say nothing has changed on the server and you visited the same website again. Your browser will again download all those resources. That will result in very slow load time and increased network bandwidth usage. Not only that, it will put extra load on the server. And this has a huge impact on frequently accessed applications. Now here is where web browser caching steps in. When you visit a website, your browser stores copies of certain resources locally on your device. So that next time when you try to access the same website, instead of downloading everything again, the browser retrieves those resources from the local cache. For example, when you visit a site like YouTube, the logo, CSS files, and common JavaScript libraries are cached by your browser. So the next time you visit, your browser doesn't need to fetch these resources again. It uses the cached versions. That's great, right? But what if something has changed on the server? How will the browser come to know when to serve the cached copy and when to fetch the resource from server? That configuration can be done at the server level. So when a server responds to a request, it can include caching instructions in HTTP headers. It can use cache-control that can be used to define whether a resource can be cached, how long it should be cached, and whether it requires revalidation with the server or not. We can also use etag. It acts like a versioning tag for a resource. Before serving the cached version, the browser checks with the server if the resource has been changed. If not, then it serves the cached version. We can also use expires. There we can specify the date and time when the cached resource becomes stale. There are different types of caching that can be implemented at various levels in our system. For example, we just discussed browser cache, which falls under client-side caching. Here, static resources like images, JavaScript, and CSS files are stored locally in the browser. That allows faster page loads and reduce server requests for repeated visits. Similarly, caching can also be implemented at the backend service level using in-memory tools like Redis or Memcached. This is known as application level caching. Frequently accessed data such as user session details, API responses, or pre-computed query results can be stored in memory. It can significantly reduce the number of database queries and improve the response time. Another critical type of caching is content delivery network caching. A CDN is a network of servers distributed globally that cache static resources closer to the end user. So when a user requests a resource like a video or an image or a large static file, the CDN serves it from the nearest edge server instead of its origin server. This reduces the latency, improves page load speed, and your primary servers are not overloaded. For example, platforms like Cloudflare or AWS CloudFront are widely used for CDN caching. Now remember one line I have been repeating in every video, there is no perfect solution. So caching is great but not without challenges. Let us see what challenges are there in caching. To explain these caching challenges, we will be using Amazon's shopping platform as an example. Think of caching like a temporary snapshot of data that helps the Amazon run faster. So what Amazon does is it stores the most frequently requested resources in the cache, so that when a user requests those resources, then Amazon services should not fetch the details from main database. Rather, it will be served from the cache that makes it easy, efficient, and quick. But what about data consistency? Let us say you are shopping for a popular gaming console on Amazon. The main database shows 100 units in stock. To make the website faster, Amazon cached these information across different servers. Now, when other customers starts buying the console, we have a challenge. Over a period of time when different customers bought consoles from different servers, that results in a mismatch in available stock in their cache. Server A's cache might show you 100 units, server B's cache might show you 95 units, and the actual database might have only 90 units. This inconsistency between the cache and the source of truth, which is database, is known as data consistency problem. Another aspect which is closely related to data consistency is staleness. Think about Amazon's dynamic pricing system. The price of a laptop might change based on a demand or some special promotional offers. Let us say the original price is $999 and the price drops to $899 due to some special promotion. But your browser is still showing $999 because that was the cached price. This issue is known as cache staleness. If you have items in your cart and one of the item goes on sale, your cart total needs to reflect that particular change. If it doesn't due to stale cache data, you might make a purchase based on incorrect information. This is why Amazon often recalculates your cart total at specific points, like when you view the cart again or when you proceed to the checkout. All those calculations will be done again to identify the latest prices so that any stale data can be removed. Now, one more important issue is there. Now we know cache is a storage which can be accessed quickly, just like we have random access memory, which is faster than the disk storage. But there is always a limit to faster data store. You cannot have unlimited fast storage, and you cannot store everything in cache. So the most important decision to make is which data should be kept in cache and which data should be removed or updated in cache and when. This particular problem involves cache invalidation. Amazon faces this challenge at a massive scale. Let us understand how. Suppose you are viewing a product with various details such as its price, stock availability, customer reviews, or any promotional offers. So when something changes, let's say a new review is posted, Amazon needs to decide should they invalidate the entire product page cache or should they only invalidate the reviews section cache, or maybe they wait for the cache to expire automatically. I'm going to repeat that one line once again. There is no perfect solution. Each of these choices that Amazon has to make has their own trade-offs. For example, invalidating the entire cache impacts the performance because it has to update every data point for that product in cache. But if we invalidate a small section like reviews in this case, then there is a risk of showing outdated information. This problem becomes even more complicated when you consider that this data might be cached at so many levels like in your browser or Amazon Edge servers and many more layers. Now, to handle these challenges, Amazon may employ strategies like they can have a different cache expiration time for different type of data. For example, the price cache might expire quickly because that is more critical, and the product descriptions might cache longer because they are not as critical as the product prices. Another strategy they can implement is cache versioning system that can allow them the gradual updates. Caching is very powerful and help us reduce latency and improve performance. There are many caching strategies which we can apply based on our requirement and application behavior. In this video, we will cover most common caching strategies which can be frequently used in system design interviews and designing a real project at work. So without much delay, let's get into it. Now, before we start with the strategies, we need to understand few terminologies which we will be using a lot during our discussion. First one is cache hit. When we request cache for some data and we found that data in cache, that is known as a cache hit. And in case we are not able to find what we are looking for in the cache, then that is known as a cache miss. Another important term is latency. Suppose we request some data from an application. The request will reach the application, which will then perform a data fetch and possibly some processing on that data before returning it to us. The total time taken from initiation of the request until we receive the data is known as latency. To be specific, this is referred to as read latency. And if we initiate a write operation, then the time taken can be termed as write latency. Another important term that we'll be using is TTL or time to live. It is an attribute assigned to the data present in cache. It denotes that the data can only be available in the cache for that specified time period. Once that time period expires, the data will be removed from the cache. Now let us begin with the caching strategies. Typically, we have these two components. One is your application where business logic is running. It can be written in Java, Python, or any other technology. Other component is your database, where all the application related data is stored. It can be a relational database like MySQL or a NoSQL database like MongoDB. In this setup, your application will connect to the database to fetch the requested data, which is perfect and expected. But when you start getting multiple requests for the same data, then fetching it from the database every time is not at all an efficient way. So what do? You introduce a fast access storage between your application and database. This storage resides in random access memory, which is way faster than accessing the data from database or an external API. That fast storage is known as cache, and the caching strategies are nothing but what role this cache will play in the overall request flow. The first strategy is read-through caching. In the read-through strategy, the cache acts as an intermediate layer between the application and the database. As its name clearly states that the read operations will happen through the cache component itself. So when the application requests data, it starts looking into cache first. If data is available in the cache, it is returned to the application. But in case data is not available, then the data is first fetched from the database and then stored in the cache, and in the end it will be returned to the application. If you use this strategy, it will simplify the application implementation, because in this application does not need to handle the cache updates. But the biggest issue with this strategy is application will never come to know if the data stored in cache is stale or fresh data. To prevent the cache from serving stale data, a time to live attribute can be added to the cached entries. Using TTL will automatically expire the data after specified duration, and a fresh reload from the database will be done whenever it is needed. Read-through caching strategy is best for read-heavy applications. Read-heavy application is an application where the number of read operations is way more than the write operations. That is, data is accessed frequently but updated less often. For example, data available in CDN systems or social media feeds. Now, if with the same setup, instead of read operations, we want to manage the write operations, every write operations from your application to database will go through the cache first. So if a write operation is initiated, it will be marked successful only after it is written to both cache as well as database. This is known as write-through caching. It is a synchronous process, so the caller need to wait till both the writes are completed. Using this, database will remain synchronized with the cache, and it will also ensure that all the read operations from cache will always have the updated data. Configuring time to live attribute is not mandatory here, because the cache will always have the latest data as all the modifications are going through cache itself. But you can implement TTL in case you are more concerned about the memory usage. But in that case, you also need to consider and handle the cache miss scenarios. The main advantage of using write-through caching is data consistency. On one side, it reduces the latency during read operations, but on the other side, due to the dual write operation, the write latency is significantly increased. Write-through is best suited for the systems which are consistency critical. For example, financial applications where cache and database must always have the latest and in-sync data. Now suppose you do not want to have cache components sandwiched between application and database. For that, you can keep it separate from the main application flow. Your application connects to both database and your cache, but the cache is not directly connected to database like it was in the previous two approaches. This is known as write-around caching. In this, when your application executes a write operation, it will be done directly to the database. So there is no role of cache till this point. Now when your application requested to read some data, then it will not directly connect to the database. First it checks if the requested data is available in cache. If it is a cache hit, that means the data is available, then the same data will be returned to the application. But what if there is a cache miss? In that case, application will connect to the database to fetch the required data. That data will be first returned to the cache so that subsequent read request for the same data can be served from the cache, and then it will be returned to the application. The main benefit of using write-around caching is that it ensures only frequently accessed data resides in the cache, and the data which is rarely or not at all used will not be stored in the cache. Also, the write operations become relatively faster as it only writes to the database. Similar to the earlier approaches, we can use time to live policy for making sure stale data is evicted or removed from the cache. Write-around caching is best for the systems like logging, where data is written too frequently and not read that frequently. In the context of read operations, this strategy of having a side cache is also known as cache aside strategy. Now let's come back to the setup where cache is not present at the side but in the middle of application and database. If I specifically talk about write-through caching, we know for every read operations we will be able to find the data in cache, which is really good for reducing the latency of read operations. But due to dual write operation, the write latency is increased significantly. So how we can improve this approach for write operations as well? What if we write data to the cache in synchronous way and return the control back to the application? And in the background, we can push the changes to database but asynchronously. With this setup, we can not only enjoy the benefits of reduced read latency, but also the write operations are optimized. Because once the data is written to the cache, it will mark the write operation successful. Database will be eventually in sync with cache. Due to this architecture, the cache acts as the primary storage here. Having said that, there is a risk of data loss. This can happen if the cache fails before the data is written to the database. So here is a question for you. In case of write back caching, how the risk of data loss can be mitigated? You can share your strategies in the comment section below. What do we remove when the cache is full? As we know, cache storage is limited because it lives in random access memory. That means we cannot store everything in cache. So when the cache is full, we need a strategy to kick out some data to make some space for the fresh entries. But the big question is, which items should be removed? That's exactly what we are going to break down today. Different cache removal strategies, when to use them, and their pros and cons. The first one is time to live. This one is straightforward. Every item gets an expiry time when it is added. Once that time is up, it is removed from the cache. Suppose we want to cache product details for our e-commerce application. So first we cache product A with TTL of 5 minutes. And then we cache product B with the TTL of 10 minutes. Now if we try to access product A after 7 minutes, we get a cache miss because it's gone after 5 minutes. But the product B still has 3 minutes left. Using TTL is super easy because it does not require usage tracking. It helps preventing memory leak by removing the data after configured time to live. So no data can remain in the cache indefinitely. All that simplicity comes at a price. Suppose there are items which are very frequently accessed, but as soon as their TTL expires, those items will be removed from the cache, which is a big problem because then it will result in a cache miss and another round trip to database to fetch the data. Now here is a quick question for you. If the cache is full and no items have expired yet, what should happen when a new item arrives? You can drop your answer in the comment section below. Another approach is least recently used, or in other words, use it or lose it. It removes the least recently used items when space is needed. It is usually implemented using doubly linked list. In that, we can move the recently accessed item to the front of the list and the removal of the items can happen at the tail. Let us understand this with an example. Suppose we have a cache of size 3. Now we add product A, B and C. Every new item getting added will be added to the front of the list. Now after some time we access product A, making it the most recently used item. So it will be moved to the front of the list. Now we have the list as product A at the front, C in the middle and B at the tail. Now we need to add another product which is product D. So based on the least recently used algorithm, product B will be removed as it was used the longest time ago. This algorithm is easy to understand and widely adopted in the real world applications. The next approach is least frequently used. In this, we count how many times an item is accessed. So when space is needed, it removes the least accessed items. Suppose again we have a cache of size 3, then we add product A, B and C with a default access count as 1. Now after some time, product A and B are accessed again and their access count is increased to 2. Now we need to add another product but the cache is full. So in this case we will check which cache product is having minimum access count, which is product C in our example. So the product C will be removed to make some space for product D. Here is another question for you. So what would happen if multiple items had the same minimum access count? What solution you can think of to solve this problem? You can pause the video for a moment and think about it. In this type of scenarios, we need to have some tie-breaking solutions. So we can opt for a hybrid approach where the tie-breaking can be another strategy. For example, along with the least frequently used, we can use first in first out approach. So when we have a tie in least frequently used, then the decision can be made using a tie-breaking strategy first in first out. Similarly, we can also use the least recently used approach as a tie-breaking strategy. The least frequently used approach is efficient for predictable patterns, but it comes at the cost of high overhead of tracking the access count. Next, we have first in, first out, or simply the queue approach. First in, first out is the easiest strategy to implement. In this, when the cache is full, it removes the oldest element, just like a queue. It is very simple and predictable with minimum processing overhead. But all that simplicity comes at a cost. Similar to TTL, it does not care about the access patterns. If an item is getting accessed very frequently, it will still be removed based on the queue position. Next approach is removing the most recently used item. That sounds counterintuitive, right? Why remove the most recently used item? But think of a music or video streaming application. If you just finished listening to a song, you probably won't replay it immediately. In most recently used, we remove the most recent item, keeping the older content that you might return to. This approach is used when recent data is short-lived. This is a very specific use case that makes it not useful for most of the general applications. Now, what if we want to balance the speed and storage efficiency while reducing the load on primary data source? We can further divide the caching into multiple layers. Instead of relying on a single cache, we can use a two-layer caching strategy, where one layer stores the most frequently accessed data. It will be the fastest one, but with a very limited storage. And the second layer stores the less frequently accessed, but still important data. It can be a little slower than the first layer, but will have a larger storage. This approach is more scalable and fault tolerant, but with the added complexity. The last approach that we are going to discuss today is random replacement, or we can say a lucky draw approach. This is the simplest and most unpredictable approach. In this, we remove a random item when the cache is full. The only benefit it provides is ultra fast speed, as no tracing overhead is there. But it is completely unpredictable, which is not good for most of the applications. Now to the final question, which one strategy you should use? You need to understand that there is no one size fits all solution. It depends on your use case. If you need freshness in data, you can use TTL. If you want to keep recent data, then you can use least recently used approach. And if frequency matters to you, then you can use the least frequently used approach. If you need storage efficiency, you can try out the two-layer caching strategy. And for simplicity, you can go for first in, first out or random replacement. What is distributed caching and how it is different from normal caching that we have been learning so far in the series? Before we start, remember this. No single solution fits all use cases, and simply watching videos or reading articles won't help you to develop skills. You need to think critically and find solutions yourself. That's why we raise questions to you multiple times during the video, and we expect you to think for any possible solutions to those problems and share with us. So try to answer the questions we ask in the video. It will help you to build necessary problem solving skills. Because when you start working in projects, that's the only thing you need to design proper solutions. Now to the main topic. So as of now, we have this simple architecture where our application connects to a cache service for faster access and a database for permanent storage. Now suppose the traffic on our application increased 10 times. Now to handle the increased traffic, we can think of few changes in our application architecture. We can think of scaling our application so that more requests can be distributed for application processing. This will reduce the load on single application server. But if we keep only one cache instance, it might become a bottleneck. With high traffic, this single cache gets overwhelmed. That will lead to slow responses or even failures. So what is the solution? The solution is distributed caching. Instead of relying on a single cache instance, we can use distributed caching to spread the cache data across multiple servers. This way, different requests can be sent to different cache servers, which will improve performance and also makes the overall cache system more fault tolerant. Let me break it down with an example. Imagine we are running an e-commerce application like Amazon, where users frequently fetch the product details. And we know the scale of Amazon. If they store all the cache data in a single server, it will definitely crash under high load. With distributed caching, different product details can be stored across multiple cache servers. So when the user requests data, it can be fetched from multiple nodes. That ensures the faster response and reduced load on a single cache instance. So if the distributed caching is so good, then why we are not using it everywhere instead of single instance cache? Just like other things, distributed caching also have specific use cases. It is similar to whether you should use monolithic application architecture or microservice scenario. Microservices are great, but they come with a great complexity to manage. Similarly, distributed caching is great, but it comes with added complexity and management. In case your application is small and has very limited traffic, a single node cache like Memcached or EHCache might be enough. But if you are running a high traffic system like Netflix, Amazon, or Facebook, then a distributed caching system like Redis Cluster, Hazelcast, or Amazon Elasticache is the way to go. Now let's see how exactly the distributed caching works in real world applications. Let me start with an analogy. Imagine a big restaurant kitchen preparing food for thousands of customers daily. It serves different foods such as grilled items, desserts, drinks, and many more categories. If all the orders are handled by a single chef, then that chef will quickly get overwhelmed, which will cause burnout and delays. And those delays will cause dissatisfied customer. And a dissatisfied customer is something which no business can afford. So to solve this problem, the kitchen can be divided into multiple sections. One for grilling, one for desserts, and one for drinks. Each of the sections will have different chefs to handle the related orders. This strategy ensures that no single chef is overloaded and the orders are served quickly. Isn't this exactly we want from our software applications too? We want no server should be overloaded and we should be able to serve the clients as quickly as possible. Distributed caching works in the similar way. Instead of one central cache storing and serving all the requests, multiple cache servers handle different pieces of data. When an application requests information, it gets routed to the appropriate cache server that holds that particular data. Now the big question is, how do we decide which cache server stores which data? There will be a component responsible for routing the request in a distributed caching system. It can be at client side, cluster side, or a proxy in the middle. But we need to understand on what basis the data will be divided. Now let's try to understand few of those approaches. The first approach is hashing. Hashing is a general technique that converts data into a fixed length value. In caching context, we use hash function to identify which cache server will store that particular piece of data. So first we need to decide on what parameter we want to divide the data on. Suppose this is based on the product ID. So we will pass that product ID to a hash function to get a hash number. Then we will divide it by the total number of cache servers and take the remainder. This will give us the server number starting with 0. If you remember, this is exactly how the hash map work in Java. Now let's try to understand this with a very simple example and with quantifiable numbers. Now suppose we have 5 cache servers and we want to cache a particular product ID. For that, what we will do, we will hash the product ID. Now let's say if the hash value turns out to be 12, then we will divide that 12 by 5, which will give us a remainder of 2. That means this particular product ID will be stored on server 2. This technique is known as modulo hashing. It ensures that the data is evenly spread across available servers. Now we just saw how basic hashing works. Taking a key, running it through a hash function, and then using modulo to decide which cache server stores the data. Pretty straightforward, right? But there is a problem with this approach. What will happen when a cache server fails or a new one is added? Now taking the same example where we have 5 cache servers and we are using our hash function to distribute data across them. Everything works fine. But one day we decide to add a 6th server to handle more traffic. Now since our formula depends on the total number of cache nodes, adding one server completely changes how the data is assigned. A product ID that was previously mapped to cache server 2 might go to server 0 now. Due to this, most of the keys are pointing to different locations. Our cache hit ratio will drop and we will end up querying the database instead. That will further increase the load on our system. Now instead of directly mapping keys to a fixed number of cache nodes, we we take a different approach. This approach is consistent hashing. Its main goal is to minimize the data redistribution when a server is added or removed from the cluster. In this, the data and server nodes are assigned a location on a ring. Based on the hash function, the data is then stored in the first cache server that appears clockwise from the position. I'll not deep dive into consistent hashing in this video because we will have a separate video on this topic. And also this is a very important topic from system design interview perspective. Now moving ahead with another approach, which is sharding. In this, we divide the complete dataset into smaller shards or pieces, with each server storing a subset of data. For example, to store user profiles in cache using this approach, we can store all users having names starting with A to M on server 1 and from N to Z on server 2. Or in a global e-commerce application like Amazon, user details can be split based on the geographical location. So in this, we do not store complete data in a single cache server, but divide it into multiple pieces known as shards and store them on different cache servers. Sharding itself is also a very complicated concept and not really easy to manage, because some shards may be accessed more frequently than others, which will result in shard hotspots. And also, if the shard's data grows unevenly, then a shard rebalancing will also be required. So we will discuss sharding completely in a separate video as well. Another approach is replication using master-slave architecture. In this, cache data is duplicated across multiple servers for fault tolerance. So unlike sharding, every cache server will have complete cache data. Out of all those cache servers, one master server handles all the writes and updates. Multiple slave servers holds the copy of data and can serve the read request. In case the current master server fails, a slave server will be promoted as a master server. In this approach, since the data is stored multiple times, it needs a higher memory allocation. Also, there is a synchronization overhead for keeping all the replicas updated and in sync. Now here is a question for you. Can you tell me how these issues can be optimized? I'll be waiting for your system design thinking in the comment section, because let me remind it again. Just watching some videos or reading some articles will not help you until you start thinking to find solutions. So go ahead and give it a try. Now, instead of opting for a single approach, we can try and implement hybrid approaches also. Because in real world enterprise architectures, we often combine multiple approaches. For example, we can use sharding along with replication. Data is sharded across multiple cache servers, but each shard is replicated to a backup server for fault tolerance. For example, we have Redis cluster with replicas. In this, each shard has primary server and a replica. Now, few final thoughts in the end to sum up what we have discussed and which approach can be used under what scenario. If you want faster reads and better fault tolerance, then you can go with replication with master-slave approach. If you want better scalability and efficient memory usage, then you can go with sharding. And if you want best of both, do sharding with replication. The data is partitioned but also has replicas for failure recovery. This is how distributed caching is architected in real-world enterprise systems. If you learned something today, don't forget to like, share and subscribe. Hit the bell icon so that you never miss an update. Thank you so much for watching. I'll see you in the next video. Till then, keep learning.